Alright, so now we're looking at a geometric series. So we have a formula given to us when we are looking to find the sum of a finite number of terms. Alright, so we're going to use for a finite number of terms. So in other words, we're looking to add up the first 8 terms. Okay? We're going to see an infinite number of terms in a little bit, so it's important to make that distinction. So these are basically the same formula. You have u sub 1 times r raised to the n. Now that minus 1 is not part of the power, okay? Just r to the n and then minus 1 all over r minus 1. And then here's the other version that they give you. Again, find it in your formula sheet. It's the fourth of 5 given formulas when it comes to sequences and series. And they tell us that r cannot be 1. If r were 1, if the common ratio were 1, then this whole formula here would be undefined, right? So let's look at an example. Alright, so we're looking to find the sum of the first 8 terms. And by the way, you can't just continue this pattern, find your 8 terms, and then just add them all up. The assumption is, the expectation is that you are using this formula every time. So on a quiz or test, we need to see the substitution to get full credit. Alright, so we're trying to find the sum of the first 8 terms. That means S sub 8. So let's use this version of the formula. So u sub 1 is my first term, so that is 2. Okay. Next we have the common ratio, which we can see here we'd have to multiply by 3 to get the next term. So my common ratio is 3. So I would have 3 raised to the n and then minus 1. Again, that's not part of the power. All over r minus 1. So be careful. Oh, you know what? I forgot to put an 8 here. So 3 to the 8. Okay. And then this is all over r minus 1, so 3 minus 1. Let's make this a little bit neater. Okay, this is an 8. Okay. So that is the n value. Okay, so n would be 8. So if we clean this up here, we can see that 3 minus 1 is going to give us 2, and that 2 will cancel out with that 2. Alright, since this is multiplication, we can divide that. So we're really just left with 3 to the 8 minus 1. Alright, so of course you're going to be allowed to use a calculator, so that's 729 minus 1. So 728 would be our final answer. Okay, our next example involves some big numbers for our terms. So we're looking to find the sum of that series. So we can see that this is our first term, and our last term is 1458. What's not immediately obvious is what the common ratio is, nor do we know what n is. We don't know exactly how many terms we're adding up. So let's start by finding our common ratio. Now, most of the time it's obvious. Here, it's not so obvious what you're multiplying by to get the next term. So remember, it's called a common ratio for a reason. We can work backwards here and form a ratio. Alright, so I can do the second term divided by the first term. And if you use a calculator, alright, and clean this up, you're going to get exactly 3/4. Okay, so our common ratio is 3/4. So let's also find our n. We can't go any further. We're not going to be able to find our sum until we can find our n. So to do that, we're going to need our general formula. Okay. So just like we saw with arithmetic, we can put our last term in here for u sub n. So 1458 is going in there. 8192 is going in for u sub 1. We said r is 3/4, and then by solving for n, we will know exactly how many terms we have, such that 1458 is the last one. Okay, so a couple different ways of actually solving this. You can use your table of values. If you wanted to input just this side right here into y equals, and then look in the table to see what x value would give you 1458. You can let the calculator do all the work for you. And we know that n must be a nice whole number since we can't have any decimal number of terms, right? Nor can we have a negative number of terms. It'd have to be a nice whole number. So you could certainly solve by using the table in your calculator. So I would encourage you to do it that way. But if you insisted on using logs because for some reason you're just infatuated with logs, we would have to first divide over this 8192, and then we have 3/4 to the n minus 1. We would then log each side. And then the n minus 1 would come down in front. And we'd have the log of 3/4. We'd have to then divide over this log of 3/4. Okay? And all of that would equal n minus 1. So if we do all of that, we would end up getting exactly, let's see, this would be 6 equals n minus 1. Well, I'm being informed that it's time for dinner. So let me hurry up and finish this because I am hungry. So n equals 7. All right, so from there we need to find s sub 7, okay, the sum. And so again, just plug right into your formula here. Our first term is 81. Okay, I'll be right there. 8192. Our r value is 3/4, which we are raising to a power of 7. Okay, and then we have minus 1. Okay, and then I don't know why I changed colors. Be right there. Yep, I hear ya. Be right there. Thank you. And then the bottom we have 3/4 minus 1. Right, that's the r value minus 1. So when you very carefully put all this into your calculator, all right, again, I would suggest doing this part first. Don't try to enter it all at once. It's easy to make a mistake that way. So just do 3/4 in parentheses raised to the 7. Hit enter. Then do minus 1. Hit enter. Then do times 8192. Hit enter. And then divide it by, well, if you don't know that this is negative 1/4, put it all in parentheses and just divide by exactly what you see there. All said and done, the sum of these 7 terms is 28,394. Okay, time to eat. All right, I am stuffed. I had raviolis, we had garlic bread. My belly is full. So, back to finishing up this video. So our last topic here, infinite geometric series. So this is, by the way, leading to our 5th and final formula. So suppose we have this infinite geometric series where we can see the common ratio would be r. Okay, we have to multiply by r to get the next term. All right, we can see that the terms are getting bigger and bigger and bigger. We say that this series diverges, okay, as opposed to converges. And we can see pretty quickly that the sum is going to go to infinity. Okay, so there's not much to really do there as far as adding up an infinite number of terms go. However, if we were to consider this second example, 40 plus 20 plus 10 plus blah blah blah, you can see here that the r value is 1/2. Okay, so we're multiplying by 1/2 to get the next term. Here we say that the sum converges. All right, it's going to approach a single value as notice our terms get smaller and smaller and smaller. Our terms are getting very, very close to 0. They'll never actually hit 0 exactly, but they're getting closer and closer to 0. Okay, so the sum is going to converge to a certain number. Okay, so we're going to reach a point where if we continue to add on numbers, it's not going to really affect the sum because it's such a small value that we're adding on. So we have a formula here. Alright, so we have the sum of an infinite number of terms. So we write this as s sub infinity, so usually that's s sub n. Well, n, our number of terms, we're saying is infinity. So we're adding on an infinite number of terms. Well, this is the easiest formula we've seen so far. It's simply the first term, u sub 1, divided by 1 minus r. Again, find it in your formula packet. This is only applicable for r values less than 1, okay? And absolute values, so we're only looking at positives, all right? Yes, your common ratio could be a negative, which means your terms will bounce back and forth between positive and negative. But this is where we're talking about things like r equals 1/2. Okay, that's less than 1. R equals 4 would not be applicable because we can see that our sum there would just be infinity. Alright? Alright, so let's use it on this example right here. Alright, if we want to find the sum of an infinite number of terms, we take our first term of 40 and we're dividing it by 1 minus whatever the common ratio is. Okay, so we have 40 divided by 1/2. Alright, please excuse my dog barking. So that is 80. Okay, so this is the sum of an infinite number of terms. Now again, we can keep adding terms onto this, but the terms are getting so close to 0 that this 80 is going to basically stay 80. Alright, we're adding an amount on that's so small it's not going to change it. Okay, so we say that the sum is 80. That's all for now. Bye-bye.